Good morning. Today we will be discussing about the history of radiology and how X-rays are produced inside a dental machine. So this is William Conrad Röntgen, who discovered X-rays in November 8, 1895. So in his honor, we are celebrating November 8th of every year as World Radiology Day. So the invention of X-rays was a serendipity. That means it was an accidental finding. Röntgen was studying the properties of gases under electric field using a Crookes tube, and then he in, uh, invented a type of unknown rays which we called X-rays. So the first radiograph was taken. This is Röntgen's lab, and this was the Crookes tube which Röntgen used while he was inventing X-ray. So the first X-ray was taken of his wife, and this is the first X-ray. So Röntgen invented X-rays in 1895 November 8, and it was an accidental inventory. So what are X-rays? X-rays are weightless packages store energy without electrical charge and that travel in space along a straight line with a specific frequency and phase. X-rays are part of X-rays are a type of electromagnetic radiation. Electromagnetic radiation means the radiation is propagation of wave-like energy without mass through the space or matter. So, and X-rays are a part of electromagnetic spectrum. Electromagnetic spectrum is electromagnetic radiation arranged according to their energy. So, what are the properties of X-ray? There are mainly four properties of X-ray, that is physical, chemical, biological, and physiochemical. There are 16 or more physical properties of X-rays. The physical properties of X-rays are they travel through space in a wave motion. In free space, they travel in a straight line. They travel at the same speed as that of visible light. As they travel through the space, they can produce an electric field at right angles to their path of propagation and a magnetic field also. They remain undetected by human sensors and they cannot be focused by a lens. They cannot be reflected, refracted, or deflected by a magnetic or electric field as they do not possess any charge. They show the properties of interference, diffraction, polarization as similar to that of visible light. They do not require a medium for propagation that we already said they propagate through space. X-rays are pure energy, there is no mass, and they transfer energy from place to place in the form of quanta. So in free space, they obey the inverse square law. That is, as the distance increases, intensity decreases. That is, intensity is inversely proportional to the square of the distance. X-rays are produced by the collision of electrons with the tungsten atoms. They have etching effect, fluorescence, penetration, and ionization. So these are the physical properties of X-rays. Chemical properties are X-rays can induce color changes on several substances or their solutions. They can cause the destruction of the fermenting power of enzymes. The biological properties are the property of excitation of X-rays can be used in the treatment of malignant lesions. As we all know, there is radiation therapy for malignant lesions. And X-rays have germicidal or bactericidal effect which is used for sterilization and preservation of food. The physiochemical properties of X-rays are photographic effect. That is, a photographic paper of film when exposed to X radiation and then they will be developed and found blackened. So, X-rays are a part of electromagnetic spectrum which have physical, chemical, biological, and physiochemical properties. So, this is Dr. Charles Edmund Kell, who is known as the father of dental radiology. He took the first ever dental X-ray of a living person who was first patient was his assistant, and the X-ray was taken in 1896 April. So while taking an X-ray, he made chiffon filling holder using a thin aluminium plate and gutta percha, and the exposure time was 15 minutes. This was the film folder which we used using an aluminum plate and the tapper cup. And these are the first ever dental X-rays taken by Charles Edmund Hess. So now moving into X-ray machine. In our daily practices and in our colleges, we use X-ray machines to take X-ray. This is the diagram of an X-ray machine. The main components of an X-ray machine is control panel, position indicating device, that is the extension arm, then the tube head. These are the main parts of an X-ray machine. So we will discuss in detail about the tube head. So tube head, this is the schematic diagram of a tube head. So tube head has a cathode and an anode. Cathode is negatively charged, whereas anode is positively charged. In cathode, there is an electron focusing cup and filament. And there is electron cloud surrounding the filament. And in the anode, there is a focal spot on the tungsten target and a copper step. There is vacuum between anode and cathode. There is a glass envelope covering the anode and cathode surrounded by vacuum containing insulating oil. There is a tube window through which the produced X-rays come out. So this is the schematic representation or schematic diagram of a dental X-ray tube head. So this is the X-ray tube head which we usually use in our clinic. First one is cathode. This is the cathode. As we said, cathode has a target, a tungsten filament and a focusing cup. It consists of an electron source, which is the filament, and a focusing cup. Electron source, as the name suggests, produces electrons by two methods, thermionic emission and field emission. Thermionic emission is also known as hot cathode and field emission is known as cold cathode. In thermionic emission, we usually use tungsten wire of 2 mm diameter and 1 cm length. The other materials which can be used for thermionic emission are cerium hexaboride and lanthanum hexaboride. The ideal properties of a thermionic electron emitter are it should have a high melting point, low work function, low vapor pressure, high electron emissivity, and high mechanical strength. So these are the 5 properties of an ideal electron emitter. So why tungsten is used as an electron emitter? Because tungsten has high melting point of 3422 degrees Celsius. It has a low vapor pressure, so it gives long life. This tungsten has high mechanical strength. That means it can be drawn into a thin wire that is quite strong. But tungsten has certain disadvantages, like it must be heated to 2200 degrees Celsius to emit useful number of electrons. That means it has low electron emissivity. So we usually add 1% thorium to the tungsten to make it a proper ideal filament material. That is, 1% thorium increases the release of electrons from tungsten. So we usually use 1% thorium mixed tungsten as a filament in cathode, which prolongs the life of the filament. And thorium is radioactive and toxic, so we only use a small percentage of 1%. So what is field emission? Field emission is not important in our case because the type of cold cathode and it does not require heat to produce electrons. It is used in carbon nanotube technology, which is very small and diameter of which is in a nanoscale. That is arranged in a bed of nails, and the electrons will be produced by the passage of electric field. Advantages of field emission is there is energy savings. It is a compact device, very small. It can be quickly switched off and on. There is no metallic deposition and the current is passed directly. But we usually use thermionic emission by hot cathode. So second one is focusing cup. So if there is no focusing cup, what will happen is it will travel in every direction. The function of focusing cup is that it focuses, that is focuses the convert is made up of molybdenum or nickel concave reflector. Electrons repel using the electric field from the whole area that is known as focal spot in the anode. So what determines the size of the focusing cup? The size of the focusing cup is determined by the size and shape of the tungsten filament that we use as a electron source, and the dimension of the focusing cup, the depth at which the tungsten filament is kept inside the slot, and the electric field associated with the focusing cup. So these are the four properties which determine the size of the focusing cup. So what determines the focal spot size? Focal spot size determines the amount of X-rays falling on the image receptor and the sharpness of image. Now, moving on to anode. So, we already discussed about the cathode. Cathode has a tungsten filament which is surrounded by a focusing cup made up of molybdenum. This tungsten filament has low electronegativity, so we add 1% thorium to increase the electronegativiity. So, moving on to anode. There are two types of anode. First one is stationary anode, which we use in our clinical practices. Second one is rotating anode. So, in case of stationary anode, there is a tungsten target of 2 to 3 millimeter size and a copper stem. You can see in the diagram that purple arrow denotes the tungsten target and the orange stem, that is the copper stem. The alternative target material other than tungsten that can be used is molybdenum, which is used in mammography. So, what target does? Target converts the kinetic energy of the colloidal electrons into X-ray photons, and the copper stem is dissipate the heat from tungsten, preventing it from melting. So, there will be exchange of energy, that is the kinetic energy of the moving electron from the electron source of cathode is converted into X-ray. There will be high production of heat in this type, and this copper dissipates the heat and prevent the tungsten from melting. So tungsten is an ideal target material. Why? It has high atomic number, it has high melting point and high thermal conductivity and low vapor pressure. So tungsten is used both in cathode and in anode. So the properties are different. In cathode, it is an ideal material because it has high melting point and high vapor pressure, high mechanical strength. And in the case of anode, it has high atomic number, high thermal conductivity, high melting point, and low vapor pressure. Next one is oil. This oil is present between the X-ray tube and the tube cylinder in the glass envelope, in between the glass envelope. It carries away the heat from the copper stem, and this oil provides electric insulation in addition to cooling of the cathode and anode. And also the casing, the glass envelope shield X-rays emitted in all directions. So we already discussed about stationary anode. Now what are rotating anodes? In rotating anodes, tungsten target is in the form of a bevel disc that rotates when tube is in operation. That is, electron strikes in successive areas of target, distributing the heat to a wider area. Other than a particular point, the anode continuously rotates an electron every time electron strikes in successive area rather than a single point. And it has a focal track rather than a focal spot. Next is lubrication. So in rotating anode, we need lubrication in order to avoid friction. So why? Because the rotation of the bearing in the rotor, that is in the rotating anode, requires lubrication. There are two types of lubrication, wet lubrication and dry lubrication. The problem with wet lubrication is that for wet lubrication, we use oil, but the oil gets evaporated, which compromises the vacuum inside the dental machine. Then there is dry lubrication. In dry lubrication, we can use graphite, but the problem is while the rotating anode rotates, these graphite bearings will wear off, which produces powder, which also destroys the vacuum. So in rotating anode, the lubrication is a problem because wet lubrication and dry lubrication can will result in compromising the vacuum, which can result in the production of X-ray. I mean, problem in the production of X-ray. So what we usually use is metallic lubricants like silver. Now, another big problem inside which we face is heat dissipation, because high energy, high kinetic energy of electrons, they are converting into photons. So there will be high production of heat also. So this heat should be dissipated. This heat is dissipated by radiating through the vacuum wall of the tube into the surrounding oil. So from the vacuum, it goes into the glass envelope, then into the surrounding insulated oil. There is absorption of heat by the anode assembly, which is undesirable. We already discussed, because if there is rotating anode, this bearings will absorb the heat, which will expand, bind, and which will cause compromising vacuum. Then there is copper stem. This copper stem connects the target to remainder of the anode assembly. It is made up of molybdenum, high melting point and 4 heat conductor. So there is focal spot in anode. Focal spot is the area of tungsten target bombarded by electrons. This most energy of electron is converted to heat, as we already discussed, and less than 1% of the energy is converted into X-ray. So if the focal spot is large, better the heat dissipated, but it compromises the radiographic details. So we already said, in rotating anode, the heat dissipation is easy, because rather than focusing on a single point, the electron strikes over successive area. There is a focal track comparing with the stationary anode where there is a focal spot. So if the size of the focal spot is large, the heat dissipation will be better. But the problem with the larger focal spot is, if the focal spot is large, the resultant image will have less sharpness, that the details will have to be compromised. So the size and shape of the focal spot is determined by the size and shape of the electron beam, and the size and shape of electron beam in turn determined by the dimension of the filament, construction of the focusing cup, and position of the filament in the focusing cup. So basically what we want is, we need a large focal spot, but it should not compromise the radiographic detail. So what we do is, the anode, rather than keeping in a straight position, the anode is inclined at an angle with a plane perpendicular to the incident beam. And this inclined angle varies from 15 to 20 degree. And this angle is known as, this 15 to 20 degree angle is known as angle of truncation. Because of this angle, when a slanted surface is viewed from the direction from which the X-rays emerge, surface is foreshortened and appears small. See, this picture depicts the angle of truncation, and the anode is at an angle. So when the X-rays come, it focuses on the anode is large, but the X-ray focuses on a single point. So the effective focal spot will be less than the actual focal spot. See here, if the effective focal spot is large, we will get a less sharp image, but we need a very good sharp image. So what we will do, we will incline the anode at a smaller angle, which results in smaller effective focal spot, and the actual focal spot size will be the same. So effective focal spot is smaller than the actual focal spot. Usually the actual focal spot size is 1 into 3 millimeters. When it is inclined, the effective focal spot size will be 1 into 1 millimeter. As the angle of anode is made smaller, the effective focal spot size decreases, which results in a sharp image. This is known as line focus principle. So, in order to get a sharp image with high resolution, we will keep the focal spot at an inclined angle of 15 to 20 degrees, which is known as angle of truncation. So, the effective focal spot appears smaller than the actual focal spot, which results in sharp image. Now, what is the role of vacuum? We already discussed the function of anode, cathode, tungsten filament, tungsten target, etc. So, what is the role of vacuum? Vacuum prevents collision of electrons with the gas molecule. So, if there is vacuum, there will not be any collision of electrons. It also prevents the wide variation in energy levels of X-ray produced, and it prevents the oxidation or burnout of the filament. So the uses of vacuum are it prevents collision of electrons, which results in high-speed X-ray beam. It prevents the wide variation in energy levels and prevents oxidation or burnout of the filament. Now, these are the parts of an X-ray machine. So, what happens in an X-ray machine, or how X-rays are produced? So, production of X-rays can be discussed under two headings. First one, at the atomic level and inside the dental machine. So, at the atomic level, how X-rays are produced, and inside a dental machine, how X-rays are produced. So, production of X-rays. So, from the cathode, by thermionic emission, electrons are accelerated towards the target and it interacts with the target tungsten target atom to produce 99% of heat and 1% of X-ray photon. That is what we already said. There is high production of heat which has to be dissipated. So, the kinetic energy of electrons are completely converted into heat energy. 99% is converted into heat energy and only 1% is converted into X-ray photons. These X-ray photons are produced by the formation of Bremsstrahlung radiation and characteristic radiation. So, at atomic level, there is two types of radiation which results in the formation of X-ray photons. First one is Bremsstrahlung radiation and second one is characteristic radiation. So, what is a Bremsstrahlung radiation? Bremsstrahlung means breaking radiation. So, it is the primary source of radiation from X-ray tube. Bremsstrahlung radiation is produced by two mechanisms. First one is direct hit interaction with the tungsten nuclei. Second one is near or wide mix interaction with the tungsten nuclei. So, Bremsstrahlung radiation is the most commonly used primary source of radiation, and it is of two types, direct hit and near miss. Direct hit is rare, whereas near miss is frequent. So what happens in direct hit? Imagine this is a tungsten target in the anode. The yellow color denotes the nucleus, and the other one is the tungsten atom with the nucleus and electron surrounding. So this is the electron coming from the cathode. This electron comes from the cathode, it hits the nucleus and there will be a momentary vibration, and in that force the electron recoils away from that position. So from the cathode an electron comes, it hits on the tungsten target nucleus, then goes from there. So in that momentary vibration, an X-ray photon is produced or Bremsstrahlung radiation is produced. That is high energy of electron comes from the cathode. It directly hits on the nucleus and Bremsstrahlung radiation of maximum energy is produced. That is the direct hit. Next one is the near miss. In near miss, what happens is an electron from the cathode comes near the tungsten nuclei, then it deviates its path and comes to the deflect to another path. So there is a deflection in the path of incident electron. So this change in direction causes a production of X-ray photon. That is known as near miss radiation. So when an incident high energy electron is come, it comes near the nucleus, then it alters path or deflect or decelerate the electron, which produces a Bremsstrahlung photon of lower energy, which is known as near miss interaction. So protons produced when electrons take a direct hit have a maximum energy equal to the voltage applied first. And if the electron, that is In near means, if the electron pass close by the nucleus, get deflected as it flows, there is loss of energy, and this loss of energy is converted to photons. And photons with continuous spectrum of energy is produced in near means. So this is the Bremsstrahlung radiation. Next one is the characteristic radiation. So what happens in characteristic radiation? In characteristic radiation, the electron from cathode comes, it hits on the innermost shell electron, and the innermost shell electron escape from the innermost cell, which creates an electron vacancy in the innermost cell. When there is an electron vacancy in the innermost shell, an electron from the outermost shell comes and occupies the space. So, the change in binding energy to come from outer shell to innermost shell. This change in binding energy is escaped as a characteristic radiation X-ray photon. So this characteristic radiation contributes only a small fraction of photons. It happens when the incident electron remove the electron from the inner orbital of the target, and that void, that electron vacancy is filled by an electron from the outer orbital. There is a difference in binding energy in the outer orbital and inner orbital. This change in binding energy escapes as characteristic radiation. So the photon with energy equal to the difference between binding energy of two orbitals is liberated, and this is known as characteristic radiation. Why this is known as characteristic radiation? Because the energy of photon is discrete and it is characteristic of the target atom. So this is the diagram of characteristic radiation. So as we explained, and high energy in photon, not photon, electron, and high energy electron from the cathode comes, it hits the innermost shell electron, and a vacancy is created. Then an electron from the outer shell comes into the fills the vacancy of the innermost shell, and this change in binding energy escapes as a characteristic photon. So this is the production of X-ray at subatomic level. So what happens inside a X-ray? How this Bremsstrahlung and characteristic radiation is produced inside a dental X-ray machine. So in a dental X-ray machine, when the filament circuit is activated, filament heats up and thermionic emission occurs. That is, inside a dental X-ray room, when we switch on, the current will be passing through the control from the power supply to the control panel. So in the control panel, the electron tungsten filament gets heats up. The filament heats up, which produces electrons, and that produces an electron cloud surrounding the tungsten filament. When this electron cloud is formed, so when the exposure button is activated for exposing these electron clouds get accelerated from the cathode to the anode. Then there is same Bremsstrahlung and characteristic radiation. So this electron strikes the tungsten target, and their kinetic energy is converted into X-rays and heat by characteristic radiation and Bremsstrahlung radiation. So when the electron strikes the tungsten target, there is production of characteristic radiation and Bremsstrahlung radiation, which in turn produces X-ray. So this is the production of X-rays inside a dental machine. So as we discussed today, we discussed the history of dental X-ray. So X-rays was first introduced or invented by Röntgen in 1895, and first dental X-ray was taken by Edmund Kels, who is known as the father of dental radiology. Then we studied what is electromagnetic spectrum and electromagnetic radiation, then properties of X-ray, and what are the parts of an X-ray machine, that is anode, cathode, what are the functions of each parts of anode and cathode, and how X-rays are produced, what is Bremsstrahlung radiation, what is characteristic radiation, and how X-rays are produced inside a dental machine. I hope everything is clear for all of you. Thank you.